Hey everyone, welcome back to my tutoring channel where I will be doing tutoring videos. In this case, it's for calculus. Today we're looking at implicit differentiation and you would use this for any graph that isn't actually a function. And for this you use both x and y values, not just x values, because that's what's part of a relation that isn't actually a function. So say you have any function in terms of x with like x squared plus sine x plus 2 and whatever. If you were to have a graph with y as well, how would you differentiate it? Say you have x squared plus y is equal to y squared. How would you differentiate this? So you would actually it's almost like a chain rule. Say y is some function of x. We'll just say y of x. That means the derivative of this function is y prime multiplied by dy over dx. Sorry, we'll say y is some like function of x and then f is some function of y. So f of y of x. So that means your function is actually just f prime of y multiplied by y prime, which is dy over dx. So essentially what you would be doing is differentiating this with respect to y and then adding dy over dx at the end because everything else is differentiated with respect to x. And so you could do the same thing with x, but you would just add dx over dx and that would just become 1. So it becomes kind of pointless. So for this type of question, x squared, when you differentiate it, it would become 2x. So you'd have to differentiate both sides to start off with. So you get the derivative of x squared plus y with respect to x is equal to the derivative of y squared with respect to x. And now using the sum rule, you can split this up. So you get the derivative of x squared plus the derivative of y is equal to the derivative of y squared. So now what you would need to do is you would find the derivative of x squared, which would just become 2x. And then you would find the derivative of y with respect to x. What the derivative of y with respect to y is the derivative of this function with respect to y is 1. So you just keep 1 over here. And then you would add dy over dx since you have a function of y and not a function of x. That's why you're keeping dy over dx, like in case I already didn't mention this. So you have dy over dx for anything that isn't actually a function of x. And so that would equal the derivative of 2y with respect to y. Sorry, the derivative of y squared with respect to y. So that just becomes 2y. And then you multiply that by dy over dx. And now the simple part, which is just algebra, is just making the rest of the function like in terms of dy over dx. And in fact, this isn't even necessary if you're trying to find the derivative at a specific point. Say you just want to find the general derivative, then what you do is you take this dy over dx to the other side, so you get dy over dx is equal times 2y minus 1 is equal to 2x, and then you just divide by 2y minus 1 is equal to 2y minus 1, sorry, 2x over 2y minus 1. But if you wanted to find the derivative of this function at some specific point, and we'll just say that specific point is 0, 1, then you would substitute this x value 0 and this y value 1 into this equation. So that would mean it's 2 times 0 over 2 times 1 minus 1. That just becomes 0 over 1, which is just 0. And you could do this with virtually any point that is known to be on the graph. And then now, using this idea of implicit differentiation, we can even find the derivative of ln x, and we'll say y is equal to ln x. This is one of the derivatives where not using the limit definition would actually be easier. And I don't know if I mentioned this, by the way, but implicit differentiation doesn't only have to be in terms of x. You could have x differentiated in terms of some other variable, which is most often t, or once you get to related rates, it might be r. It really depends on the question. But anyways, back to this. You could even find the derivative of ln x with implicit differentiation. So if ln is the inverse of of e to the power of x, that means x is equal to e to the power of y, because its inverse is y is equal to e to the x. So this basically, these two functions are the exact same thing. So now it would be a lot easier to differentiate this function implicitly, because these are both functions that we actually have rules for. And so that means we take the derivative of x with respect to x, and then we take the derivative of e to the power of y with respect to x. So that means the left side would then become 1. And the right side, if you take the derivative of this function with respect to y, you get e to the power of y. And then you multiply by dy over dx. So that means dy over dx is equal to 1 over e to the power of y. But we didn't have e to the power of y in our original function. But right here, that's x. So that means e to the power of y and x are the same thing. So we can substitute x back, and we get the derivative of ln x as 1 over x. So using implicit differentiation, we found that the derivative of ln x is equal to 1 over x. And using the chain rule, you could probably also find out that the derivative of ln of 3x is equal to 1 over 3x times the derivative of 3x, which is just 3, which also happens to be 1 over x. In fact, you could keep any constant over here, ln of ax, and your derivative will still be the same, because using log laws, ln of ax is equal to ln of a plus ln of x. And then when you differentiate this, which is a constant, you get 0. When you differentiate this, you get 1 over x. So yeah, that's the derivative for the log function, well, the natural log function. But next video, I'll get to the derivatives for exponential and log functions that don't have a base of e. Thank you for watching this, and keep practicing math, and please drop any feedback in the comments, whether it's about the audio quality or about my actual teaching style.